Okay, back to Charles Coulomb. Charles Coulomb is famous. He had the unit of charge named after him because he did some experiments to determine the behavior of electric force. And he figured out a few things. First, he figured out that the force is proportional to each of the two charges. You have the two charges and you multiply them together, the force is proportional to that. And the other thing he discovered is that this force is an inverse square law. If you have two things that are twice as far away, they'll have 1/4 the force. 3 times as far away, 1/9 the force. 4 times as far away, 1/16. 100 times away, that would be, what, a 10,000th of the force, etc. So you have an inverse square law. Are you familiar with a law that is proportional to some fundamental constant and behaves as an inverse square? You should be. The law of universal gravitation. Fg equals gm1 m2 over r squared behaves in exactly this way. It turns out that Coulomb's law also behaves in exactly this way. He figured out this law, which looks super similar, right? Fe equals k q1 q2 over r squared. What have we got? The q's are the charges, r is the distance between them, and k is called the electrostatic constant, or sometimes Coulomb's constant. This constant is enormous. The universal gravitational constant is very small. Coulomb's constant is, well, depending on which class you're in, you're going to use 8.99 times 10 to the 9, or you're going to just use 9.0 times 10 to the 9 Newton meters squared per Coulomb squared. And just like big G being really, really tiny tells us that gravity is super weak, Coulomb's constant K being really big tells us that electricity is a very, very strong force. One detail that makes me a little nuts is that on the AP reference tables there's an absolute value around Coulomb's law. And that's a little frustrating to me because that positive or negative sign tells you something. If you multiply a positive by a positive, you get a positive. Multiply a negative by a negative, you get a positive. But a positive times a negative gives you a negative. If your answer in a Coulomb's law problem is negative, then it's an attractive force. And if your answer is positive, it's a repulsive force. Why they would absolute value that away and get rid of it, I don't really know, but they did. So to give you an idea of just how much charge a Coulomb is, let's say you're sitting near a classmate, too near for COVID times. You're sitting 1 meter away, okay? So you two of you are sitting 1 meter away from each other. If I were to take 1 Coulomb of charge off of one of you and put it on the other, what force of attraction would occur between the two of you? If you plug in K, 9 times 10 to the 9 Newton meters squared per Coulomb squared, times 1 Coulomb times minus 1 Coulomb divided by 1 squared, you get 9 times 10 to the 9 newtons. That is a crazy amount of newtons. That's over 1 million tons of force. You would just... It could never happen. I couldn't take a Coulomb off because every time as I pulled electrons off, they get harder and harder to pull off. But if I could snap my fingers and do it, the whole town would just implode towards you. So a Coulomb is an enormous amount of charge. But the average human body contains over, say, 2-3 billion coulombs of charge. But for every Coulomb of positive charge, they have a Coulomb of negative charge. So the average human body is neutral. But there's a whole lot of charge just hidden right under the surface of our reality that is pretty impressive if you can unleash it. And something I forgot to mention in the last video. I mentioned if I pulled a Coulomb of charge off, the whole town would implode towards the person. Well, isn't the town neutral? Well, it turns out that positive charges and negative charges attract each other, right? But any charge will actually attract a neutral object because of polarization. So check this out. If you rub your head on a balloon and you stick the balloon to the wall, why does it stick? The balloon is charged, yes, but the wall is neutral. Well, inside the wall you have both positive and negative particles, right? If you take a negatively charged balloon and bring it toward the wall, the negative charges move away. The positive charges are left behind. And Coulomb's law says that the force depends on distance. So when the balloon comes near the positively charged wall, the negative balloon sticks to it. because it is being repelled by the negative charges in the wall, but they've been pushed further away, and so the force isn't as strong. So when two objects attract, that is not proof that they're both charged. That's proof that at least one of them is charged, or they have opposite charges. If two objects repel, that is proof that they are both charged and that charge carries the same sign.